Hey folks, welcome back to the shrine for the hand-me-downs of the industry. Thanks for visiting, thanks for checking in. I'm gonna talk about another measurement project that I've been working on. This is a cylinder for an engine. The cylinder was manufactured in China. This is based off of a Honda Cub. As you probably know, the Honda Cub is the vehicle that they produce the most of in the world. As far as I know, it's around 100 million pieces since 1968. Compared it to, for example, the VW Bug, which is only about 40, maybe 45 million vehicles. So this one is what they call a big bore kit. I bought it for because several reasons. One of the most important aspects is the rib orientation. So this is axial with the piston, and that's really important for my application. And they call it big bore because this is a 54 millimeter bore. What I've done so far is I 3D scanned this, and I built a 3D model, and in the model I have a separate part for the cylinder liner, and I have another part for the overmold, which is aluminum. And one of the things that I didn't know so far is the bolt pattern. The 3D scan gives me a good idea, but I really wanted to measure it. So if you look at my drawing here, let me zoom in. So this is my drawing. For those knowledgeable in the field will recognize these markings here. So these are what's called datums, and you can see there are 3 datums. So there's datum A, datum B, and datum C. So these datums in relation to each other will constrain the part, so they will remove all 6 degrees of freedom. Now let's talk about the datums. If you look at this part, I was really struggling to find a surface somewhere on the side that is machined, and I only found this surface here. So this is a machined surface. So initially I set it as datum A, and you can see that here. So it comes from the cylinder, the center line of the cylinder, to the machine face. And it's relatively easy to establish. Once we establish the cylinder, then we can find the center of it. The second datum B is this plane here. So this is also a machined plane, and we can rest the cylinder on that plane, butt it against some kind of plate that has a hole, properly sized hole, and that is going to locate the cylinder. So if the hole matches this diameter, that can be datum C that you can see here. So that's the outside diameter of this liner. And I did some initial measurement, and I realized that this boss surface is not giving me a good reference, a good datum. And I just measured it, some of the parts, and compared it to these edges here. So you can see that this cavity here has this edge, and that's a line, and then the outside one is an arc. So this is a line. And so I was trying to figure out a better way to constrain it. And I was going along the lines that when this cylinder is initially machined, what we had in the past are targets on the print back in the 70s and 80s and earlier than that, that especially called out for chucking and locating surface. So if you imagine, this liner is initially machined, so that's a machined part. Okay, and it has this stab on it. So when they put it in a cavity and they overmold the aluminum, this already has a good datum. Both this guy and this guy are machined, most likely. And so if we constrain the part on those 2 datums, it still can rotate. And so for the initial machining operation, they need some kind of datum. And so I was trying to poke around on the bottom here, and I found this edge. What I did is I put my little square to the edge, and sure enough, it's a nice straight edge. Now if you lift it up like that and you look through right here, you can't really see light. So that told me that this edge here, this surface, which is about 2.5 millimeters deep, that can be used as a locating surface. So originally I had a plate, and this plate was machined to accept this diameter. And what I did here is I added this slider. Okay, so all the slider does, it's spring-loaded and it can move in and out, as you can see. So I can move this slider out, insert the cylinder, bring it back, and this surface right here is gonna go against this surface, and it's gonna align the cylinder properly. So once we have that alignment, you know, the cylinder, this plate is gonna be in a vise, in a mill vise, and then the cylinder is gonna be placed like so, and then the slider is going to align the cylinder, and I'm going to make sure that the cylinder is laying flat on this surface so it's not cockeyed. And so once I have that, then I can come in with the coaxial indicator and locate the bore. And once I locate the bore, I can zero out the readout on the mill, and then I can come in. I already know the approximate locations for these holes, so I can come in with the indicator and try to find those holes and basically adjust the table X and Y to make the indicator 0, and then that's when I'm in line. So that's what I did on this piece here. So this was just a test piece. I have 6 of these cylinders, so I'm going to repeat the measurement, and once I have all 6 cylinders measured, then I can create a table and I can average it. And I created a drawing and I numbered all the different dimensions for every hole. And then I can build a table, and then I can average it out and see if this measurement is giving me a reasonable good measurement. If this measurement is acceptable, if this measurement is repeatable. So I know it's only 6 data points, but that will be a really good indication. One of the things that I don't like about this dimensioning scheme is the way the holes are dimensioned. So there's not a master hole, and then every other hole would be dimensioned from that, but they actually use the bore. So this tells me that there is all kind of fixturing going on in a plant where these parts are manufactured, and so they are not measuring, you know, each hole relative to this, but what they have is they have a plate similar to this one, which has pins, and those pins are fairly, you know, tight tolerance, and they can just put the cylinder on the plate and then use some kind of clamps to clamp it down, and that's it, and they can machine it. So one more bonus thing here, I have on the top 1 threaded hole here, and if I come in with the indicator, you know, the indicator is going to go into that helical groove and it will give me some error. So what I have here, this is a shoulder screw, and this is an M6 thread, and this is a nice cylindrical surface here. So I can wind this in, you know, and make sure that it doesn't wobble, and then come in, maybe use a little spacer here, and then come in with the indicator and basically indicate this surface here, this cylinder. And so we are going back to the Bridgeport CMM, and we're gonna do one more measurement. So for the noise, my phase converter is making noise. So what do we have here? Bridgeport 1952, equipped with digital readouts, chai included. I installed them. It hangs off of the RAM. It's got a scale along the x-axis. It's got another scale here along the y-axis. And it's reasonably good. I tested and checked it with indicators and it worked fine. I installed the plate that I made earlier in a vise, and I made sure that this corner here matches, so I can remove the plate and reinstall it, and then I can get the center bore reasonably well centered. I installed the coaxial indicator. It's got this tip. You can see that when I deflect the tip, the dial is going to move. Okay, and if I turn it on, you can see it's going around and the dial is not really moving. Okay, so we are right on center. If I move any of the axis, that dial, so let's move this axis. So I hate to do that because it was already centered. You can see when I move that axis, that dial is gonna come out of a zero position. So now I'm moving back, and you can see it's still moving. There you go. It's not moving anymore. It's just getting hung on some kind of rust or something, debris. So we are reasonably centered. So now I'm gonna go and zero the X and zero the Y. So now all this, the center of this hole is centered up with the digital readout. So I replaced the tip. Now we have this short, stubby tip. I'm gonna raise the table until the tip is at the same level. Just like that. And now I'm gonna move the table to the first position. So you can see here's my print. Now I oriented the print the same way. So here's the cutout for the cylinder. Here's the cutout on the print. There's dimension number 1. So we're gonna go for dimension 1 and 2. So 26. So we're gonna move it 26. It's showing negative. Don't worry about that. It's just relative to the position that it was in. So 26. And then we're gonna move the table in. Okay, so we're gonna get 26, 26, both on X and Y scales. And then bring it down. Okay, so what we need to do is have a little bit of play here. Okay, so that much play. So we move the probe into the hole. You can see that the needle is moving back and forth. So now we're gonna move the X and Y axis to make sure that we stabilize the needle. And this requires moving both axes, both the X and the Y. You can see the dial is barely moving, and so that means that the center of the machine, the center of the spindle, is aligned with the hole. So now I can turn the spindle off and look at the readout. So look at this. So this is supposed to be 26 millimeters, so it's 5 microns off. Okay, 5 microns. And then this is supposed to be 26 millimeters, and it's 230 microns off. So 230 microns is about 10 thou. So we're going to write those numbers down and go for the next hole. So there's hole number 2. You can see the indicator is reasonably stable. We're going to turn it off and then go and evaluate. So these are the numbers. So the X direction is 2616, should be 26 per my print, and the Y direction is 20.83. Here is hole number 3, and I'm trying to get the indicator needle to be like 1 division, which is 5/10. Okay, so that would be around 12 microns. So that looks good. And here's the data: 24,175, 2269. So on my print, this 22.5, and this is 24. So here's hole number 4. You can see that it's moving half a division, so it's around 6 microns. Stop the machine! Machine stop! So let's see what we got on the readout. 2445, 2588. So it should be 24.5 and 26. So 24.5 and 26. So those are reasonably good numbers. So now you can see that the point is riding on that cylindrical surface that's attached to the bolt, and I managed to pull it within 1 division. These are the dimensions. The Y is 0.09, so 90 microns, and then the X is 62.2. So this is 90 microns off of the print, and this is 200 microns off of the print. So the first set of measurements is done for cylinder number 1. So we're gonna go and do the rest 5 of them. So I'm measuring cylinder number 4 right there, and this hole here, hole number 3, and you can see that dial is pretty much dead on, and if you look at the indicator, it is showing 24,000, and that is something, that is tolerance. I'm on the last measurement, cylinder number 6. Changed the little thing here, added these 2 screws to hold the cylinder down to the plate, because I could feel it on the first trial that it was wobbling. So I used these plastic spacers so not to mar the surface with the screws, and it worked fine so far. I finished all the measurements and the numbers are in. You can see that so these are the different cylinder heads. I have 6 of them, and then these are the different dimensions, and I marked the dimensions on the print, and the first 8 dimensions related to these 4 holes where the through bolts are retaining the cylinder to the engine block. And then we got a couple more other dimensions. So for example, this oil gallery hole I wasn't able to measure precisely, but this other one here, which is a mounting hole, this is a mounting hole here, that came out pretty good. So if you look at the numbers here, I averaged it, and then I have maximum, minimum, and then I have a symmetrical tolerance. So if you look at the numbers, you can see every tolerance basically is below 0.2 millimeters. So I consider that a pretty good measurement, you know, with the equipment I have in-house, pretty good repeatability. So again, some of the dimensions are off for this large oil gallery hole, but overall it's a good measurement. So there you go, return of the Bridgeport CMM. Hope you guys enjoyed the video, and if you did, please give me a thumbs up, and if you like the channel, please don't forget to subscribe. See you next time. Bye.